right. So I believe like the exam is over. So how was it? How was the exam?
It was fine. Hello, can you hear me?
Yes, I can. So did you have any difficulty? I thought those are straightforward things I have
Uh,
said.
no, that much.
No,
I couldn't.
it was tough, you mean?
I couldn't find any symmetry in the spring problem to use Noether's theorem.
There are symmetries.
Energy.
Yes, energy is conserved. And what? So basically for each of the constant of integration you found, those are actually conserved quantities. So you're supposed to get 4 quantities out of that. Hmm?
Yes, initial position.
Yes, initial position, initial momentum, and yes, for each of the particles. So those are the conserved quantities. So for each of the coordinates, you'll be able to find 2 conserved quantities, and that will also include like conservation of energy as well. Okay. Hi, Carl.
My password. It worked.
Okay. Are you planning to present something on the presentation day?
I was thinking of talking about the last physics experiment I did, and some of the equipment I built for that. That's I will think. But yes, so the answer is yes. I'm thinking about it.
Yeah, that'll be great. That'll be great. So to the other students, please try to present something. It's an opportunity. And also, like if you this one is optional, so you have an advantage here. So if you do bad in the exams, so some extra point will be added for those presentations. So probably it will be secure your position in the general relativity in brief as well. So try not to like spoil the opportunity. Okay. So yes, what did we learn last time? We learned vectors, right?
Yes.
And saw that if we have a curve and if we have a parameter on that curve defined, probably say sigma or lambda, so say sigma, final sigma, this one. So then the tangent vector to this curve would be v equals to dp tilde, which is basically point in space, how many dimensions you need, over d sigma, right? Okay, this is what we had. Also, we learned something about one forms, right?
Yes.
So associated with this same coordinate, you have actually one interesting thing, that is d sigma here. So this d sigma, it's a new object that's unlike vectors. they transformed in oppositely, but they have similar properties, like they form vector space at least. So let's call it alpha. So like that, we learn two kind of quantities. So now it's better to build some intuition on those two things, and uh, find some quantities that actually we used to think those as vectors, but now basically they'll be appeared as one forms. So first, let's build the intuition. So we saw, let's erase this thing and start with the usual definition, like the coordinate definition of the basis vector and basis one forms. So we saw that for coordinates, if we have a system like x mu coordinates, then each of the bases of those system will have like e mu vector, that is delta p tilde by delta x mu, right? This is what we learned last time. And also we defined our omega say nu, which is a lower bar, equals to
G.
gx mu. So okay, let's set up few notational like convention here, notational convention. So when I'm writing upper bar, it typically means vectors or vector basis, and when I'm writing lower bar, it's a one form basis or one form itself, one form or one form basis. And when I'm writing a tilde overhead, it means it's a multi-component object. It has many components in it, but it's not a linear one like a vector. So when you take derivative of a multi-component object like this, you get a vector.
Okay.
Okay. Okay. So now, if we had a vector v, and then we wanted to split in terms of those coordinate bases, then we would write like v mu e mu, like that, right?
Yeah.
And also, if we had a one form, say alpha, we would probably split in terms of coordinates like this: alpha lower mu, or lower nu, say nu, omega nu. Is that clear to everyone? So when I'm writing upper index, it has a specific meaning. So be careful about indices where I'm writing. When I'm writing lower indices, it's also have meaning. So be careful. Like, I'll explain it why I'm writing this way, but for now, just for a moment, just consider those are by convention, that for vector component I'm writing upper index, and for one form component I'm writing lower indices.
So basically, one form is dual basis or dual vector.
Yes, we explored that last time, right? It lives on dual space instead of vectors, like tangent space.
Yes.
Okay. What else did we learn last time? How to find the components, right?
Yes.
So to find the components v mu, all you need to do is to perform a piercing of v with what? Omega, right?
Yeah.
If you take this thing, then you get vector components. And similarly, for if you want to like alpha nu, what do you do?
Then I will take VF.
No, you take alpha and e nu, like
Yeah.
that.
Yeah. The
And
basic.
that piercing thing, that's actually defined through, if you want to define it through the coordinates, then it's like say omega nu and then E mu, doing a piercing on that will produce Kronecker delta nu mu, right?
Yeah.
Okay, and also we learned this thing is a linear, this piercing thing is a linear. So if we had a df, or actually df over d sigma, say, if we want to do this thing df over d sigma, then we have to do this thing, pierce df with delta p dp over d sigma. You could write delta as well, it doesn't matter here. So on sigma parameterized curve, you are actually taking derivative of f.
Yeah.
Okay. What else did we learn last time?
I think that's all.
That's all, but there's a like how to expand one forms, that's we learned as well. Like for df, we would be able to expand like this, delta f over delta x mu dx mu, right? As we already know that this is basically the same relation like chain rule relation, but it's a more rigorous form. That's why we are writing like a lower part, that's all. It carries all the information of derivative of f, so it's basically a big object, not just a scalar number. Oh, but you need to remember one thing, that mathematicians won't write these lower bars, or they won't do boldface one, but physicists want to do that, and MTW does that. So gravitation text does that. So like gravitation text actually doesn't distinguish between these vector objects and one form object. They write everything as bolds, but mentioning this is a vector, this is a one form. But as we are writing, and we are actually had to choose between like upper bar, lower bar, so we could use two different things for two different ones, right? Okay, this is the thing we learned so far. So now it's time to build some intuition first, also see few more things, how to evaluate the norms, that's one thing, and another is what happens when you change the coordinate. So let's learn the mathematics first, then we'll build our intuition on it. So mathematically, so what happens when you go from one coordinate system, so probably this is your space here, so now you had this coordinate system and probably you do not like that, so you have replaced this coordinate with this one, this new set. So what happens then? So basically your coordinate definition, those were x, now it becoming x prime, all the coordinate changes to x prime.
Yes.
So if we want to write down the transformation relation, we should write like this: x, say 1 prime. Actually, if we use lower indices, then like probably we would write like x1 prime like this. But here we are using upper index for coordinates, so we have to write like this. It might look odd, but that's the standard notation. So x1 prime is a function of x1, x2 up to xn, like that, for n-dimensional system. And so for x2 prime, as we are writing everything in terms of primed coordinate, so sorry, unprimed coordinate, like the older one, so x2 prime is a function of x1, x2 up to xn. and so on. Like that. So we should have n transformed coordinate as well. So the final relation would be like this: xn primed equals to xn prime is a function of x1, x2, and x up to xn. Is that clear to everyone?
Yeah.
So this whole n number of equations are packed into this one. Or you could write like this: x prime is a function of older x's. You could write like that as. So by writing this, we actually mean there are these kind of things. But typically, you want to write like this one. Or, yeah, okay. There is a better notation for that. We'll introduce it later because we are not going to use it anywhere now. So let's introduce it later. Okay. And another notation is like, it could be written like this: x, say mu prime, is a function of x nu, where mu prime and nu equals to 1 to up to. It could be written like that as well. Is that clear to everyone?
Yeah.
Okay, so what happens to the one form objects like this type of object? What happens to them? And also what happens to the vectorial objects like the above one, this one? So all we need to explore what happens to the basis first, right? What happens to the basis first? So if we had e mu prime in primed coordinate, the vector basis, that would definitely be delta p tilde over delta x mu prime. Do you agree with that?
Yeah.
Is that clear to everyone? That in new coordinate system, it'll be just like that.
Yeah, just mu replaced with mu prime.
Yes. So now those are coordinates and those are related, like old and new coordinates are related. So we could use multivariable chain rules, right? So by adapting Einstein's sum, we could actually expand this derivative like this. Take derivative of p tilde in terms of x older coordinates, x nu, and then delta x nu over delta x mu prime, like that.
Yeah.
So if we do that, then what is this part?
E mu.
E nu, right?
Yeah.
So we could write E nu, and then we have our other part, that is x nu by delta x mu prime. So we have the transformation relation between the vector basis. So E mu prime equals to delta x nu by delta x mu prime multiplied by E nu. So as you can see, it's a linear relation. The older vector basis and newer vector basis are related linearly, right? Just by this matrix.
Yeah.
So it will become an object. It will be a tensorial object as well. But for now on, actually, we're just dealing with this way. We'll explore it in more detail. Like, we are not like learning everything at this moment. So yes, so we'll discuss this thing more deeper than we are doing here now. Okay, So this is we have got. Then what happens to the vector components? What happened to the vector components? So if we had a vector v, it could be written in terms of older basis like this, v new e new, right, like that, or could be written in terms of newer basis, that is v mu prime, which we mean like mu component of v in newer coordinate, multiplied by e mu prime, like that.
Yeah.
So we could expand our e mu prime in terms of this relation. So we could write like this. So from this relation, what we can conclude? Can you conclude this?
V mu is equal to V mu prime.
Yes. V mu
Bx.
prime. Or I'm going to write
Yes.
it later. I'm going to write the derivative, like the matrix first, then the other part. Prime V mu prime.
Yeah.
Okay. So, but I want to write V mu prime, not V nu. So what do we do?
Inverse.
Just multiply by something, not just multiply, like operate the opposite partial derivative that nullify this part. So okay, so let's make sure we know few things, that delta x mu not primed over delta x nu equals to Kronecker delta mu nu. Is that clear to everyone?
Oh, well, I have a question. What is the difference between Kronecker delta mu nu and Kronecker delta nu mu actually?
It's just the indices that we have used. It doesn't matter like which way we use the indices. So it's just names, like mu, those are the name of the component.
Yeah, that means which operation we have done first and something like that.
No. Like which component we are talking about. So Kronecker delta mu is actually have mu coordinate on here and mu coordinate over here. So like when you write each of the components, so probably it has like delta 1 1, delta 1 2, delta 1 3. So here, as you can see, like the mu is varying, not the nu. But if it were here, then probably if you just vary mu, it will be like delta and fix nu to 1, then it will be like this. Like that.
Yeah, mu is changing.
Yes. So think about it's a matrix component. It will be easier for you now. We'll understand in a more deeper way. But for now, just understand that it's just a matrix component.
Okay.
Okay. So if we understand that, then what you can do is we can actually do this thing as well. Delta x mu prime over delta x nu prime. That means just take the same derivative but in newer coordinate. That would be the same old Kronecker delta, but the indices are written different name with a different name. Right?
Yeah.
Okay. Then what we are going to do, we are going to multiply the whole thing, like say multiply delta x kappa prime by delta x nu v nu equals to delta x kappa prime by delta x nu by delta x mu prime v mu prime. Is that clear?
Well, I have a question. The prime is not over mu. I think the index is mu, isn't it? But the prime is over x mu. That means the
Yes,
x mu prime is the new coordinate. But
yes, yes.
mu is mu.
So
That is the coordinate.
yes, definitely you could write like this. You could write like this. That's not a
Right.
problem. But there is a problem when you're writing like mu prime as indices. So probably you'll be like tempted to like sum over like mu and mu prime. So it's better to keep that. So even we started with like x prime like mu, x prime mu like
Right.
that. But our
Yeah.
change of notation, actually we are using like this. So when we are just same x but with a different kind of index like mu prime indices, we understand that it's the newer coordinate.
But is
It's
that
just
a
hmm?
but is that a new coordinate? It's just our old coordinate in new indices.
No. We understand it as a new coordinate.
How can you understand as a new
So
coordinate?
point is it doesn't matter what you write. It matters what you express with that writing,
Uh,
right?
okay. That means we are
So
denoting it by this.
yes.
Okay.
So just be careful. Like we are not going to actually confuse between these two things like x mu and x mu prime. Here probably mu runs from 1 to n. Also here mu prime runs from 1 to n. But remember, these two things are actually this one older and this one the new coordinate. So it's for the convenience. That's all. You could use that. You could like, okay, I want to be so adamant with like x and x prime. Then you just write down your prime over there, and sometime like you'll be confused between these two kind of indices. Like you have two kind of objects and two kind of sums, but you are treating similarly. So it'll be difficult for a while when you have a lot of. But when you write like this, those will be distinct. Like indices will be distinct.
But we could just use another letters for index.
Yes. You could use another set of letters. That could be useful as well. Yes. A set. You need to find a different set.
Yeah.
The same set will be difficult. Yes.
Can you use that? Can we use that now? Because
Uh,
x mu and x mu prime is little bit confusing.
no. It'll come in really handy. So if we want to change that thing, it's gonna screw up later. So don't do that.
Okay.
So there is a reason like GR people has set up this kind of notation. There is a reason. So when you do a long calculation, it's better to stick with this kind of notation, this particular notation. It's better.
Okay.
Okay, so now see that x nu and delta x nu, that's basically expansion of a chain rule, which is basically delta x kappa prime by delta x mu prime.
Yeah.
And then you have v mu prime. So the notation of like putting indices outer is that now you understand that sum over mu is actually running here and here. But if you dump your prime on x, you'll have like a little bit difficulty understanding this two part. yes, obviously then you will have like V prime as well, not V mu prime. Okay, so now so this delta x kappa prime over delta x mu prime, what's that? Here, right? Those should be Kronecker delta, because when you differentiate the same coordinate with respect to itself, it's 1, and when you do with other one and any other one, it will be 0, because those are totally independent. So it will be Kronecker delta kappa prime by Kronecker delta kappa prime mu prime, then V mu prime. And we know when we sum like this kind of thing, it's summed over. So we learned earlier that for Kronecker delta, all you have to do, you have to replace, like write down the same object, but replace the index to the newer one. So the other one actually, on which the sum is not going on. So yes, we got the transformation relation for V kappa prime, which is V prime, like new for new coordinate, vector component for new coordinate, that is delta x kappa prime by delta x nu V nu. That's the transformation relation.
Okay.
Yeah.
Okay, so now we actually let's make a list over there. So V mu prime would be delta x mu prime over delta x nu V nu, right?
Yeah.
Let's make a list over there. Okay, so now do the same thing, do the same what happens to the change of the coordinate, that same calculation for one form as well. So for one form, we have the basis. So bases are like omega nu, right? And definition of omega nu is d x nu, right? So in new coordinate, say omega mu prime would be by definition dx mu prime, right? And dx mu prime can be expanded in terms of the older coordinate, that would be like delta x mu prime by delta x nu dx nu, right?
Yeah.
And dx nu is nothing but omega nu, so we can write delta x mu prime over delta x nu omega nu. So we can list it up here. That is our omega mu prime is, it transforms like delta x mu prime by delta x nu. So what we mean by transforming omega, we have to be a little bit more precise. Like, just let's finish it, then I'll explain it in full detail. Okay, so can you find the correspond, like if you have a one form alpha, if you have a one form alpha, can you find the transformation relation for the code components of this alpha? Can you find that? So what would happen, like if you have alpha mu prime, what should it be? Can you find that using the similar manner we did here?
Alpha mu prime, omega mu prime.
It will be?
Oh, no. Yeah, sorry. I have to find it.
So let's, if you're having trouble seeing this, let's expand, right? Okay, so we can expand our alpha in older coordinate or newer one, right? So in newer coordinate, it's like alpha mu omega mu prime, and older coordinate it was alpha nu omega nu, right? But this newer one in new coordinate, alpha mu prime omega mu prime is what in newer coordinate we just derived. So we can substitute. That is delta x mu prime by delta x nu omega nu.
Yeah.
And that is obviously the alpha nu omega nu. So equating two sides, what we can conclude? Alpha nu, this part equals to this part, right? But we want this thing, not alpha nu. So what should we do? Multiply both sides by this thing, delta x nu by delta x kappa prime equals to alpha mu prime delta x mu prime by delta x nu by delta x kappa prime. Right?
Yeah.
We just multiplied on both sides the same thing, like delta x nu by delta x kappa prime. So this one, what happens to this? So it can be written, as you can see, like these two things are same. So chain rule applies. So by chain rule, we can apply write like this: delta x mu prime by delta x kappa prime.
Yeah.
And delta x mu prime by delta x kappa prime, what's that?
Kronecker delta.
It's Kronecker delta what? Kronecker delta
Mu prime, kappa prime.
Kappa prime, yes. And then if we write down the sum, what do you get? What happens? It's
Alpha kappa prime.
Alpha kappa prime, right? So we got the result. Alpha kappa prime is this thing, right? So delta x nu by delta x kappa prime alpha nu, right?
Yeah.
So let's write down it over there in the list that we were making. So alpha mu primed equals to delta x nu by delta x mu prime alpha nu, right? Okay, so do you see any similarity between these transformation rules? I think you can see the whole thing. Do you see any similarity?
Yeah.
What similarity do you see?
For one form components and for vector basis, mu prime, the prime coordinate is
Yes, for vector basis and for one form
components.
components, that is this one, right?
Yeah.
This one and this one, they have similar transformation properties. And vector components and one form basis, they also have similar transformation uh, properties, right?
Yeah.
So what does it really mean? So now it's time to explore that. What do we mean by the specific transformation rule? And okay, let's do it in a sloppy way. So say you have a coordinate transformation rule that is just multiply by 2. The older coordinate is multiplied by 2. That means your x1 prime is basically twice x1, and x2 prime equals to twice x2, and so on, right?
Okay.
So if is that, then can you find the matrix relations? Like um, let's find this thing first. So delta x
Identity
mu
matrix with
prime. Yes. So if we construct a matrix out of it, if we take those derivative and construct a matrix, then what should it look like?
diagonal, all the diagonal 2 and
It will be diagonal and what? So yes, the 1 part, like here, this one is nothing but delta x 1 prime by delta x1, right?
yeah.
So it will be like just 2, like that. So, and the next one here, this one basically delta x 2 prime by delta x 1, right? Yes. So what's that? That is basically 0, right? So we'll
it will
have
be
like this.
diagonal matrix with all the elements of diagonal S2.
Yes, like that. Do everyone agree with that?
I do not understand why only diagonal matrix will have value 2.
Sorry. Yeah, this is because of our transformation rule. We defined our transformation rule to be like the new coordinate x1 prime equals to twice x1, and x2 prime equals to twice x2, and like that.
Okay.
So we are taking those derivatives and finding this is basically the Jacobian matrix, probably we call it. If you construct a matrix with the derivative, it's called the Jacobian matrix. So that's what we have written.
Okay.
And that's obviously, as Shubho said, it's basically twice multiplied by just the identity matrix, right?
Yeah.
So okay, if you multiply identity with something, it's just that. And so this thing, as you can write this relation like this, x mu prime is equals to twice x mu, right? This is the full form. We could do this thing in component wise as well, like just keeping those indices as well.
But here is the problem with a confusion with the indices again, because if mu prime is an index, mu prime and mu are two different indices, then
Yeah, here actually we, as I said, like we understand what it means.
Okay.
We just understand what it means. Like here we mean like x1 prime equals to twice x1. That's what we mean. So obviously, if we compactify, you just vary the mu. So yes, that's what it looks like.
Okay.
And you could do the same thing with your x prime mu as well. So yes, that's correct. Okay, so obviously now if we take this derivative delta x mu prime by delta x nu, it will give me twice Kronecker delta mu nu, right?
Yeah.
Both notation has like its advantages and disadvantages. So this is the one case like where this notation, like mu prime notation, it's disadvantageous. Okay, but we know what we're doing, so yeah, it's not a problem. So okay, so just by doing that, our v mu prime would be like twice Kronecker delta mu nu v nu, which is twice v mu, right? So when we have a relation like this, that the new coordinate is half of the older one, so we could write like this as well. So x1 equals to half of new coordinate is half of the new coordinate is the older one, right? That's what we are writing. We just halved the coordinate. That's what we did. Right?
Yeah.
So when we do that, the vector components become the double one, right? It becomes doubled.